Hello, today we're continuing with the A-Level Physics Revision series looking at two mechanisms which are used in medical physics, ultrasound and magnetic resonance. Ultrasound makes use of an effect called the piezoelectric effect. If you take a crystal such as quartz, that crystal will have this quality that if you were to compress it, or indeed stretch it, you have an impact on the crystalline structure that actually adjusts the way in which the negative and the positive ions are formed, and in that distortion you actually create a potential difference. So the idea is, very simply, that if you take a crystal and just leave it there, then there's no voltage. But if you either squash it or try to stretch it, then you'll get a voltage. And if you put silver connectors at either side of the crystal, then of course you can put that into some kind of electrical circuit. Now, what can cause the crystal to be stretched and compressed? Well, the answer is sound waves. Sound waves are coming in and they are remembering vibrations in the air. They are longitudinal waves where the air is vibrating. So if you've got a crystal here and you've got vibrating waves hitting it, then that crystal is going to be one moment compressed and the next moment released and stretched. And that means that you will get a voltage changes from the silver attachments to the crystal. Ultrasound is used, and that means that you're using frequencies of more than 20 kilohertz. Which means you are beyond the audible hearing of most people. So there's no unpleasant sound in your ear, you just can't hear it, the frequency is too high. So you can use this device for both producing and detecting sound. If you actually pass an electric current through the crystal, it will cause the atoms in the crystal to vibrate, and those vibrations will come out as ultrasound. That is, the frequency of the vibrations is about just over 20 kilohertz. So that's a way that you can create the sound. Similarly, if you've got sound coming in, it will cause the atoms to distort, and that will create a voltage, and that can be detected. So the same piece of equipment both generates the ultrasound and detects the ultrasound. Now, the way this is used to work relies on the fact of what happens when a wave, any wave, can be a light wave, but it can also be a sound wave, hits a boundary between, say, skin and a bone, boundary between one organ and another organ. Wherever there is a boundary, wherever the medium changes from one to another, then an incoming wave will do two things. Part of it will reflect, and part of it will refract. The reflected wave, the angles of incidence will equal the angle of reflection, and the refracted wave will have an angle of refraction which is governed by Snell's law. And obviously the intensity of the incoming beam will be equal to the intensity of the refracted beam and the intensity of the reflected beam. And what we usually call these is, this is called the reflected beam, and this is called the transmitted beam, because it actually gets transmitted through the medium. So the usual way that we describe this is IR standing for the reflected beam and IT standing for the transmitted through the medium beam. Now there's a concept called acoustic impedance, which we give the letter Z, which is rho times C. Rho is the density of the medium, and C is the speed of sound through that medium. And if you're going from one medium to another, one medium that has Z1 as its acoustic impedance, and the other has Z2 as its acoustic impedance, then the ratio of the reflected beam, that's this one, the ratio of the intensity of the reflected beam to the intensity of the original beam is given by Z2 minus Z1 squared divided by Z2 plus Z1 squared. And that ratio is known as the intensity reflection coefficient. Now the difference between Z1 and Z2 for different parts of your body is actually quite small. But the difference in impedance between air and parts of your body is very large. And so you do not want any air to be in the way when you are sending a sound signal into the body and then receiving the sound signal back out of the body. And that is the reason when ultrasound is being used that the nurse or the doctor will put a gel on the surface of the skin and then put the instrument on that gel, so there is no air between the instrument and your skin, and that way the sound wave will transmit into the body, which is what you want it to do. And then all that of course is actually happening is that you put your device on somebody's skin. There will be various things under the skin, various organs that you may be trying to get some handle on, and the sound will come down. It will be transmitted, but it will also be reflected, and then it will be reflected there. And so what happens is you send out a pulse of sound. Some of it is reflected, but some of it is transmitted, and then when it hits another boundary, some of it will be transmitted, some of it will be reflected. And so what you do is you get sound, the sound pulse comes back at different times depending on whether it's been reflected from the first or the second boundary. And that voltage pulse can be sent to an oscilloscope where it can create a picture, a three-dimensional picture of what you're actually seeing under the skin. And if there is any irregularity there, then that should show up. Of course, you have to recognise that the further the sound pulse goes before it is reflected, the more likely it is to be attenuated, that is, to lose power. And so in this device, or in the electronics that follow it, you have to compensate for that so that this signal coming from this boundary will be stronger than this signal coming from this boundary. And in order to get a proper picture, of course, you want those strengths to be the same. So this signal coming from this boundary will need to be amplified so that it's comparable in strength to the signal coming from that boundary. The intensity of the sound at any point is given by the I0, which was the original intensity coming from the equipment, times e to the minus mu x. And mu is the linear absorption coefficient, or the linear attenuation coefficient. And so the percentage of the transmission against x is going to look like this. It's an exponential decay. And rather like nuclear decay, it's a half-life. So in other words, after half the time, after the half-life, you have half of what you had before. In each case, this is 1x, 2x, 3x. And in each case, the amount that you have left is half what you had before. We turn now to magnetic resonance, which used to be called nuclear magnetic resonance, but I think it probably lost the term nuclear because it gave the idea that it had something to do with nuclear power stations, and it has absolutely nothing to do with that. The nucleus in question is the nucleus in the atoms inside your body. Nuclei have a property called spin. And if there are odd numbers of protons in a nucleus, then that spin will cause the atom to behave like a tiny magnet. Hydrogen has only one proton, and therefore hydrogen, which of course is a major constituent of your body, since most of your body is made up of water, and water is H2O, and H is the hydrogen bit, that means that the water molecules, the hydrogen elements of the water molecules, act like little magnets in your body. Now, if you put your body in the presence of a massive, and I mean massive, magnetic field, then what will happen is that all those magnets will tend to line up, all those little hydrogen atoms will all line up the same way. But they don't, of course, go from being in this position to being vertical and just go like that and stop. anything that moves like that is going to what's called precess. In other words, it's going to move from here to here, but it's going to what's called precess. It's rather like a top. It wobbles. And so all of these are not precisely lined up this way. They're all wobbling around like precessing tops. And the frequency of that precession is called the l'amour frequency. And that is usually in the radio frequency range of the electromagnetic spectrum. Now, if we send in a radio frequency wave from external, from the outside, which happens to be the same frequency as the precessing l'amour frequency, what will happen is these atoms will gain energy. They will resonate. They will resonate with this wave and they will precess with the more energy. And then when you take the radio frequency wave away, the external radio frequency wave, then these atoms will settle back to where they were before, and that's called the relaxation. And the time it takes them to do it is called the relaxation time. And the energy that they absorb from the incoming radio frequency wave, once you take that wave away, the energy that's been absorbed will now be dissipated as the atoms precess, and that will generate a radio frequency wave which comes out of the atoms. So how does it work? Well, you have a huge, as I say, a huge magnet. This is usually 1 Tesla, which is massive. And you put the patient on a bed inside that magnet, and that means that all the hydrogen atoms in the patient are going to line up and precess with the l'amour frequency. You have to have 2 additional magnets, which are called, which produce a non-uniform field. And the reason for those is that that will enable you to detect whereabouts in the body you're getting information from. And then around the bed, you have your coil. And that coil is going to be the generator of the radio frequency information. And it also will detect radio frequency information. So it's the source of this radio frequency that will cause the hydrogen atoms to precess with more energy. And it's also the means to detect when you switch this radio frequency source off and the hydrogen atom nuclei relax and emit a radio frequency signal, that is also detected by this coil. So basically all that happens when you're sitting inside the magnetic resonance imaging is that the radio frequency coil is switched on, that sends out a signal, that causes all the hydrogen atoms in your body to precess and resonate with this radio frequency coil. You switch off the current, now the nuclei can relax, and in doing so they emit a radio frequency signal. That radio frequency signal is detected by the radio frequency coil and is sent then to an imaging machine. And the fact that you've got these 2 magnets here enables you to detect whereabouts information is coming from, and that enables you to construct some kind of image of what's going on inside the body. Hello, today we're continuing with the A-Level Physics Revision series, looking at 2 mechanisms which are used in medical physics: ultrasound and magnetic resonance. Ultrasound makes use of an effect called the piezoelectric effect. If you take a crystal such as quartz, that crystal will have this quality that if you were to compress it, or indeed stretch it, you have an impact on the crystalline structure that actually adjusts the way in which the negative and the positive ions are formed, and in that distortion you actually create a potential difference. So the idea is, very simply, that if you take a crystal and just leave it there, then there's no voltage. But if you either squash it or try to stretch it, then you'll get a voltage vibrating. So if you've got a crystal here and you've got vibrating waves hitting it, then that crystal is going to be one moment compressed and the next moment released and stretched. And that means that you will get a voltage changes from the silver attachments to the crystal. Ultrasound is used, and that means that you're using frequencies of more than 20 kilohertz, which means you are beyond the audible hearing of most people. So there's no unpleasant sound in your ear, you just can't hear it, the frequency is too high. So you can use this device for both producing and detecting sound. If you actually pass an electric current through the crystal, it will cause the atoms in the crystal to vibrate, and those vibrations, and if you put silver connectors at either side of the crystal, then of course you can put that into some kind of electrical circuit. Now, what can cause the crystal to be stretched and compressed? Well, the answer is sound waves. Sound waves are coming in, and they are remembering vibrations in the air. They are longitudinal waves where the air is